Silakan nyalakan dulu kameranya. Saya tunggu. Takna, Mas Reza, Mbak Nadia, Mbak Salwa, Mbak Natasha, Alicia, Mbak Amira, Mbak Raisa, Mbak Nadira, tolong dinyalakan kameranya dulu. Nanti saya sambil absen, biar saya nggak absen 2 kali nanti. Tunggu sebentar ya. Mas Alvin, kalau nggak nyalakan kamera, saya anggap Anda tidak hadir. Mbak Nadira, Mas Fahri, Mas Ryan. Oke, sebelum saya mulai, alangkah baik kita berdoa dulu. Semoga dengan agama dan kita masing-masing, agar yang kita pelajari ini bermanfaat untuk banyak orang. Berdoa saya persilakan. Amin. Berdoa tidak pernah selesai. Oke, thank you. You can turn off the camera. Okay, in today's class, I will share part of the syllabus. We talk about the introductions of coding and emulation. First of all, so we have to know the definitions. What is the coding? Why should we learn about this issue? So after you learned by today's class, you will know what is Quantitatory, what is important tool for improve the business, what are the example of the different coin systems, because there are various of coin theory that we can applicable. Also about the component of coin systems, and so if you're talking about the coin theory, it's all about the exponential distribution or exponential theorem, and about the stochastic models, same last week. First, the definitions of coin theory is from the mathematical analysis of the QI and waiting times in stochastic systems. So it's used extensively to analyze productions and service process exhibiting random variability in market demand, arrival times, and service time. That's why if you're talking about the coin theory, it's about we have to measure the arrival times of the customer and about the service times as well. So the QI arises when the short-term demand for service exceeds the capacity. So most often, we're talking about the service business. So we have to make sure that every customer can be have good experience about the arrival times and about the service times as well. So we have to know about if long-term demand for service, if large more than that, the capacity required will be explode. So that's why we have to make the system, the good system that we can make our customers have good experience in our business. So the capacity problems are common industry, and one of the main drivers are process redesign. So we have to net the balance, the cost about the increased capacity gains and the gains of the increased productivity and service. So the queuing and waiting time analysis is particularly important in service system because lack cost of waiting and a lost sales due to waiting. So for example, the prototype in the county hospital. So patient arrive by ambulance or by the end of the cart. So we have to know, for example, if the patients come to the hospital, how long they have to wait until doctors come to serve. Yeah, there's quite many applications in Quantitatory in the business area. So there is some of particular definitions if you're talking about the Quantitatory. First about the FIFO. FIFO comes to first in, first out, or first come, first serve. So it means the customer are served in the order they arrive in. So it's about the VIVO. And the second about the LIVO or SCVS means last in, first out, or last come, first serve. So it means the customer are served in the reserve order to the order they arrive in. And the third is about the zero. Zero means service in random order. It means the customers are served in the random order with no regard to each other. And the last one is about the PNPN. PNPN is a priority service. It means including preemptive and non-preemptive. So it's about the priority queue. So if later, if they many the applications of the queuing theory in the business, they should be including by these four categories: Vivo, Zero, or PNPN. So there is large of example of the queuing systems in the business area. First, about the commercial queuing systems. It's about the commercial organizations serving external customers, dentists, bank, ATM, gas stations, plumber, garage. If talking about the transportation systems, the applications about the vehicles or customer observes. For example, vehicles waiting at toll stations and traffic light, trucks or ships waiting to be loaded, taxi cabs, fire engines, elevator, and buses. So if the applications of the client problems in the business service system is about the customer receiving service, which is the internal organizations providing the system. For example, inspection stations, conveyor belts, and also computer support. Last but not least, the applications of the queuing systems in social service systems is about the judicial process, the the hospital, waiting list for organ transplant, or student dorm rooms. So there's many the applications of the queuing system in the real world. Later of this class, I will give you the homework. So you have to make provide the example more despite of this slide about the queuing theory. So the component of the basic queuing process, we have input source here. So it is about the population. So we have to measure the arrival process, the queue configurations, queue discipline, and service process. So once there's a patient, there's also maybe some of the people come to some place. So for example, they want to queue, and they have to wait until how many times until they can get the service and also serve from the particular officer. That's why later if you're talking about the queuing theory, is about the steady state process. So we have to know that our system in the office or the business is good enough or not to our customer or our business. So we have to make sure the queuing system is good. So the component of the basic queuing properties, first about the population. Populations means the form which customers or job originate. The size can be finity or infinity, so the letter is most common. And also how about the homogeneous? For example, this type of the customer of jobs or heterogeneous. It's about the several different kinds of customer or jobs. So there's our population. And second issue about the arrival process. The arrival process, we have to measure determinants how, when, and where customer or jobs arrive to the system. So this we have to calculate the arrival process. And also the important characteristic is the customer jobs inter-arrival times. So we have here inter-arrival. First, we have arrival times, and second, we have inter-arrival. Third, to correctly specify the arrival process requires data collections, interval times, and statistical analysis. That's why we have to collect first our data. The data already collected, so we can analyze by using the queuing theory. So we can get the information our business is steady state or not. The queuing configurations means to specify the numbers of the queue, because if we only have 2 servers in office, so for example, maybe in the 2 servers, they only can handle for customer or for patient. So sometimes we need many service line. We need also needs many server to handle the customer. So the queue configurations also have to thinking about their location, and also about their effect on the customer behavior, bulking and engines, and also their maximum size. That's why we have to make sure that our serving or our serving times is quite reasonable. So if the customers come to our business, so we can make sure that they can wait patiently. So this about the increase the business. Here, for example, For example, here our customer, so we can make the simulations of the queuing. So for example, we have the full server here, so we can make some of the simulation, how to make the system is quite good um to our business area. For example here we have the full server, and this one is the multiple queries. This for example is our customer or the patient. So patients comes around from this line and they have to wait until server's customer, or you can make like this. This about the single query. So we only have the single line for the customer or the patient. So later you can maybe make sums of combinations of simulation how to find the good the querying system. So we can make like this, the multiple query or the single query like this. So this the advantage and also the advantage of about the multiple line and single line. First, the multiple line that the service provide can be differentiated. So it comes with the supermarket express lines, the example. And the second about the labor specialization is possible. Also about the customer has more flexibility, and about the bulking behavior might be different. So the super medium length lines are less intimidately than one very long line. So if you're talking about a single line, this is the example of the Vivo, first in, first out. So it's Vivo. So it guarantees fairness if we're talking about the single line, the advantage. And the second about the non-customer anxiety regarding choice of queue. So this is the advantage of the single line. And also avoids cutting in the line process. And so but the most efficient setup for the minimizing time in the queue. And the last but not least about checking line switching is avoided. So this is the advantage of single line at same time about the multiple line. The component of the basic querying process, we have the service mechanism. It's about the involve on all several service facilities with one or several parallel service channels. We're talking this about the servers. So specification is required. Also, the service provided by server is characteristic by its service time. So it's we have to record and typically the data gathering for the statistical analysis. And most analytical querying models are based on the assumption of the exponential distributed system. That's why I'm already talking about, if you're talking about the Quantitatory, the application should be exponential distribution or Poisson distribution, because there is only, for example, one zero or one data is about the count data. So the distribution should be fit is exponential or Poisson. And the required discipline is about the specifies the order by which jobs in the query are being served. So most commonly, the simple is for the Vivo, first in, first out. But the other rules we can make by Livo, SPT, and IDD. Later, you maybe have to find in Google Scholar what is the applications of this example disciplines, Livo, SPT, and IDD. And can entail prioritization based on the customer's type. So this is about the query discipline. About the mitigating effect of the long quest. For example, if the restaurant are referred by people to bar for use pagers, we have to know, for example, make some place that our patients, our customers can wait patiently. So we can provide some spot, maybe TV or magazine space, so they can wait patiently. And or we can using by customers as a resource. So for example, patients filling out medical history from while waiting for a physician. And about the making the customer wait comfortable and distracting their attention. So like this, maybe we can provide some of the drink at restaurants, computer games, internet stations, food court, and so on. And also the expand reasons for the wait. So this is the mitigating the effect of the lying quiz. About the provide pessimistic estimate of the remaining waiting time. So this about the wait seems shorter if a time estimate is given in the mitigating effect. And the last about the be fair and open about the query discipline use. So this is the example of the common querying system. First, here we have a customer. So this is the line process or the query line. So customers. So they have to wait until they can get served by the server or the officer. So this is our line customer. And the service facility, so for example, they have a server, so this customer have to wait until they can be handled by the server or handled by the officer. So this is import the client system until they can out from this client system. So this the commonly seen client model in summary. So it's about the service times as well as interval times are assumed independent and identical distribution. So that's why time by time of each of the customer have to wait. So it's their time will be different. So that's why it should be identically distribution. So every patient is have different distribution. And here the commonly used notation is principle. We have the ABC. A means the interval time distribution. B means the service time distribution, and C means the number of parallel server. So we can have first this information. Letter 2, data analysis. And also about the commonly used distribution here. That's why if you're talking about the quantitative models, it's about the exponential distribution or Poisson distribution. That's why we have the Markovian process. I hope you don't forget about the last week. We have the stochastic process. So the quantitatory is part of stochastic process. And D means deterministic distribution, and G means the general distribution. So for example, we have the MMC. MMC means the quant system with the exponential distribution, service and interval times, and C server. So it means the MMC. Markovian, and C is number of the server. Sometimes number of server can be 0, 1, 2, or until infinity. We move to another slide. So the learning objective of this course is about the example by the trade-off curves of the cost waiting times and cost of service. Also described of the basic client system configurations and 3 parts of client system. So that's why I already explained the basic by the last slide about the client population, the client itself, and the service facility. So that's why I explain it firstly before I go further by this slide. We're talking about analyze a variety of operating characteristics by waiting lines for single channel models with exponential service times and infinity cutting population. So that's why I already tell you about the single line and multiple line. So you already learned about that. And last but not least, about the analysis variety of the operating characteristics of waiting lines for multi-channel models with exponential service times and infinity scaling population. So you already learned about that. So the my first slide is about the summary of these chapters. So I try to explain again the introduction. So the quantitatory the study is about the waiting lines. So that's why we have to measure the waiting lines for our customers in business area. So the one of the oldest and most widely used quantitative analysis techniques. So this quite old school models and stochastic process. And they have 3 basic components. We're talking about the querying process. First, about the arrival itself, about the service facilities, and the actual waiting lines. And the analytical models of waiting lines can help managers evaluate the cost and effectiveness of service system. That's why we have to make our system in steady state. So once our system is steady state, we already have the good system with the specific number of the service of the server as well. So sometimes if we have many server, we have to pay more for them. So that's why we have to make sure we have to make the good simulations that our system is steady state. So about the waiting line cost, so most waiting line problems are focused on finding the ideal level of service a firm should provide. So I already explained about this. So we have to make sure the simulations is steady state. And the second about the generic service level is something management can control. That's why if something that can control, so we have to maximize that benefit. And also we have to minimize that risk. So once we can control, we can do about that. And often try to find the balance between the two extremes. So we have the example here, large staff and many service facilities. That's why high level service but high cost. So our system should be steady state. We have to make sure that our service or our server is quite good enough to handle the customer. And the second, the minimum number of service facilities could be lower, the service cost, but may result in dissatisfied the customer. So sometimes if we only have the few number of the server, so they cannot handle the customers quite good. That's why our customer should dissatisfied. So we don't want to do that. And the last about the service facilities are evaluated on their total expected cost, which is the sum of service cost and the waiting cost. So we have to find the service level that minimize the total expected cost. So that's the issue about the netting line cost. So this is our diagram here. We have to some information about the cost, the optimal service level, and the service level here. So we can have much of information here about the total expected cost, it's quite large or not, about the cost of providing service, and about the cost of waiting time. So we have to minimize the cost waiting time. We have to minimize the cost providing service. We have to maximize the total expected cost. So we can get the optimal service level with this criteria. And here about the Three Rivers Shipping Company. So Three Rivers Shipping Company operates a docking facility on the Ohio River. So on average of 5 ships arrive to unload their cargoes each shift. So the either ships are expensive. So this is our information. More staff can be hired to unload the ships, but that is expensive as well. So we have to minimize the number of the total cost. And the Three Rivers Shipping Company wants to determine the optimal number of teams of stevedores to employ each shift to obtain the minimum total expected cost. So this is our information. For example, here we have a G information or G variable, the average number of ships arriving per shift. You have also average time ships. We have total ship. We have estimate cost. We have the value of ship. We have also have team salary or service cost and total expected cost. So later you can make the practicum later with my assistant about how to calculating the quantitatory. So here we can do various of the self-working load. Here, for example, we have the 1, 2, 3, 4. So after we analysis, so the optimal cost should be by 2 server. Here, 2 server with they can handle by 5 ships. They can handle by 4 hours waiting. And total ship hours is $20, and also others information. So we can find which some simulation or some server with the optimal cost. So this is the idea of the queuing theory. About the characteristics of queuing system, we have the 3 parts of queuing system. First, the arrival or input to the system, sometimes referred to as the calling population. So I already explained about that, about the calling populations. Second, about the queue or waiting line itself, and also about the service facility. So these 3 components have certain characteristics that must be examined before mathematical queuing models can be developed. That's why before we have to analyze our queuing systems or the waiting lines, we have to have this information, our variable about arrival systems, queue waiting line itself, and the service facility. Just like this information. We have the effort number of ships, we have effort time each ship to be unloaded, we have total ship hours. So this is our information before we can calculate to find the optimal cost. So we have to get that variable first before we analyze this. Also about the arrival characteristic, have 3 major characteristics here. So about the population sometimes that can be unlimited or infinity or limited or finity. So this is our population. And second, about the patterns of arrival. So but the arrival itself is according to unknown patterns or can arrive randomly. So this is our characteristic. And the second, about the random arrival generally follow a Poisson distribution. That's why I repeat many times if you're talking about the queuing systems, the basic distribution should be exponential or a Poisson distribution. That's our goals by using other statistical models. So if you're talking about the behavior or ripples, these have three issues. First, most common models assume customers are patient and will wait in the queue until they are served and do not switch line. So this is our characteristic of the waiting lines. So customer should not switch lines. So they have to wait until the server can handle the customer. The bulking refers to the customer who refused to join the queue. So they have the information about the bulking. And the last one is about the reneging. So the customers enter the queue but become impatient and leave without receiving their service. So this is reneging customer. They already join the line, but just leave without receiving their service from the server. About the waiting line characteristic, can be either limited or unlimited. And the quiet discipline refers to the rule by which customer is line service. So that's why if you're talking about the queuing system, the most properly applicable is the Vivo, first in, first out. So this is quite reasonable and quite fair if talking about the queuing system. So the most it is the application of the single line, Vivo, first in, first out. Other rules can be applied to select which customer enter which queue, but may apply Vivo once they are in the queue. So this is the rules of the Vivo about the first in and first out. Here I already explained as well about this, about the configurations of the queuing system. We have single channel systems or multi-channel systems. So single one channel systems means the one server, and the multi-channel systems means the multiple server fit by one common waiting line. So sometimes they have advantage and also disadvantage. So later you can make the discussions. What is the advantage and disadvantage? So I already tell you about the advantage about the single channel systems and multi-channel systems. Later you can make what is the disadvantage about this issue. SAMs, we have the patterns of service times. We have single phase system here about the customer receive service from just one server. Or multi-phase system, the customers go through more than one server. So this is example of the pattern of the service system with a single or multiple. Here the basic of the system configuration. First, of the single channel or single phase system. So they have a variable here. They have to waiting line here at our queue. So we have a service facility here and departure after service. And here the example of single channel or multi-phase system. We have the variables here. So this is our waiting line, queue line. So type 1, the service facility. So maybe we can provide the service facility here and make the queuing line again. And type 2 also the service facilities and departure after service. So this is the example of the single channel and the multi-phase system in the queuing system. Or we can make like this. So sometimes the customers come to our office or business area. They have to wait in this line or queue line system, and can be choose first serve facilities 1, serve facilities 2, or serve facility 3. So this is the multi-channel, but in single phase system. So we can make the departures after and get the service. So this is the example. And also we can make like this. So they come to our business area, variables, and waiting the queue system. And here we have the type 1 service facilities. We have type 1 service facilities 2. So this only the multi-phase system for each service facility from the type 1 and near type 2 until the departure after the service. So this is an example of multi-phase system and multi-channel. So but the service distribution could be constant or random. So service pattern can be either constant or random, and constant service times are often machines controlled. And also, you're talking about the generic service times as are randomly distributed according to a negative exponential probability distribution. So this is the example of the exponential family in statistics. The last what the analysis should observe, collect and plot the service time and the data to answer The observations fit the assumed distributions when applying these models. So before we further analysis the statistical analysis, we have to fit first our data. This data can be fit with the exponential distribution or the Poisson distributions. So you can using the Kolmogorov-Smirnov method. This sum of the applications by further analysis by using the weighting line, but we can using by Kendall notation here. So Kendall notations means annotations for the querying models that specifies the patterns of the variable, the surface time distribution, and the number of channels. So Kendall notations can handle this issue. So in Kendall's notations, we have three symbols of three information here. First, about the variable distributions, about the surface time distributions, and the number of surface channels open. So we have this type of the informations in the Kendall notation, similar with my first slide. And the specific letters used to represent probability distribution. Here we have the M as the Poisson distribution, D we have the constant deterministic rate, and G we have the general distributions with mean and variance known. So we have to know what type of the mean and the variance of our data we can set. Here, for example, if we have the single channel model with the Poisson, sometimes if you read many paper, so you will not confuse again. So MM1 means the single channel model with the Poisson variable. So we can set the MM1. And if, for example, we have the second channel, so we can set 2 here, MM2. MM2 means the surface times with the 2 channels. And how if we have the 3 channel system with Poisson variable and constant surface time? So we can set as the MD3. So I already give the information how you can put the DG 1, 2, 3, 4 and others. So you can use that by your specific problems. And the last here, for example, a 4 channel system with Poisson variables and normally distributed surface times would be MG4. That's why here we have 4 channel system. That's why we have 4. For example, here we have Poisson distribution. You can set G here, and also about the normal distributed system. So you can what the MM1, MM2, MD3, or MG4. So it depends on your research question later. So this have 7 assumptions of the model. So first, variables are served on a vivo basis, first in, first out, and there is no bulking or reneging. So this is the assumption if we using the MM1 about the single channel models, Poisson variable, and exponential surface in times. So we have the MM1, MM2, MD3, MG4. So every this type of characteristic has their own assumption. So you should careful before you perform this analysis. So this the assumption that you have to fill before you analysis. Second, about if using the MM1, there is no bulking or reneging. And also the variables are dependent of each other, but the variable rate is constant over time. So our variable time or variable rate should be constant time by time. And the variables follow a Poisson distribution. So if we have variable data, so should be fit by the Poisson distribution. And about the surface time as variable independent, but the average is known. And so about the surface times follow a negative exponential distribution. And last, about the average surface rate is greater than the average variable rate. So this assumption of by using the single channel models with the MM1. So when the assumptions are met, we can develop a series of equations that define the bias operating characteristic. Here we have, because we using the Poisson distribution. In Poisson distributions, we only have 2 parameters. We have lambda and mu. Lambda means the number of the variable per time. So this is the mean number of the variable time. And mu means the number of the customer or units served per time period. So you have 2 parameters in the Poisson, lambda and mu. So the same time period must be used for the variable rate and the surface rate. So we have to make sure how much our lambda and how much also our mu. Here we can calculate the average number of the customers or units in the system. So we have L here. L means the number of the customer. So we can measure by lambda divided by mu minus lambda. So you can get information of the number of the customer. And the second, we have the W. W means the time of the customer spends in the system. So we can calculate the W by 1 per mu minus lambda. So we can get the information by lambda to calculate the customer spends in our system. Also, about the first number of customers in the queue, we have the LQ. So LQ means the lambda power 2 divided by mu. So we can multiply mu minus lambda. So we can calculate the LQ here, or the customer's first number in the queue or the waiting line. So we can calculate the L, W, and the LQ. So we have to calculate the first time. So it's WQ. So we can calculate how many the customer spends waiting in our queue system. So you can calculate by W and Q. And the last, we have to calculate the probability. So that's why if you know about the basic stochastic process, the goal is only to get the probability value. So the probability value can be steady state or not in our waiting line. So you can, using rho, we can get this information rho by lambda divided by mu. So but the mean and the variance itself. So we can get informations by the probability, but service facility being used in our system. And we have the percent idle time. So we have the P0 here. So P0 here means the percent idle time. So we're talking about the probability value should be start from the 0 until 1. So you can using this information to calculate the percent idle time. Also, we can measure the probability by customers in the system is greater than K. So this is our criteria. If our number of customers in the system is greater than K, so we can using Pn more than K. So you can using this information. If our customer in the system is greater than K or our server. So you can using this information to get that information. Here, for example, we have Arnold Modeler shop for simulation. So our issue that Arnold's mechanic can install movers at the rate of the 3 per hour. So this is our information, 3 per hour. So this is our system or our mu. And the customer arrive at a rate of 2 per hour. So it is our lambda. So it's quite easy. So we have lambda 2 and mu 3. So we can calculate the L, W, and the address information. So L, so we can get the result is 2. So 2 cars in the system on average. So the system can be handled only 2 cars in average. And W, we can get the 1 hour that an average car spends in the system. So we can get this information as W. It's easy. Here also we can using the LQ. So after the analysis, we can get the 1.33 cars waiting in the line on the average. So this is the line waiting line in the average. So maybe you can use put it as 1. So because there is no 1.33 cars, so you can put 1 cars waiting in line on the average. Also, we have to calculate the WQ. So it means the 40 minutes average waiting per car. So once per car can be handled by the server, they have to wait until 40 minutes for the waiting time or the waiting line. And rho means that we have the 0.67% of time mechanism is busy. So you should be careful. If we have more than 0.5 the percent time, so there can be our systems cannot steady state because there are a huge of number customers can become, but we only have limited system or we have only limited server. So sometimes in the business area, it quite be difficult if our budget is quite limited, but how we can maximize that? So this is the example of interpretation. So you have to be careful if we have rho here, probability more than 0.5. So that's because it's good. Our business maybe have the many customers come, but we cannot handle there with the fast or quiet in the handle business. So this is quite the issue in the business area. Here we can make the informations by using the P0. So probability that there are 0 in cars in the system. so 0.33. So once the probability here is close to 0, so it means that our system is quite busy, or our server is not good enough to handle the customer, because we have the limited server to handle the patient or to handle our customer. Here we can make the probability with the k cars in the system. So later you can calculate with easily because we have this information. So you can make the combinational comparisons from the k is the cars start from 0 until the 7. So this is the example. So later you can make the simulations by the Excel in practicum. Here you can make maybe in another practicum class, you can using by Excel KM to solutions for the Arnold's Marble Shop. So I think if you're not using the KM, you can do that because it's very, very easy in Excel. So we sometimes no need the sum of the macro in Excel. So you can calculate by manually. It's quite easy. We're still talking about the Arnold's Marble Shop. So this is about introductions cost into the model. So Arnold wants to do an economic analysis of the client systems and determine the waiting cost and the service cost. And total service cost is the total service cost. We have the number of channels here multiplied by cost per channel. So here we have the total service cost means the MCS. M means the number of channels, and CS mean of the service cost or labor cost of each channel. So this is our information. Total service cost, MCS. So you can calculate this total service cost. Here we have the waiting cost when the cost is based on the time in the system. We have total waiting cost here, total time spent waiting by arrival multiplied by cost of waiting. So we can get this information. Or you can short by this mathematical by lambda W CW. So this is our information mathematically to waiting the waiting cost or to calculate the total waiting cost. So if the waiting time cost is based on the time in the query, so we can calculate by these informations W, the lambda, WQ, and CW. So we can calculate this waiting cost by delivering example. Here, so the total cost of the current systems when the based on time in the system. So we can using as well by this information. Total cost can be calculated by total service cost plus total waiting cost. That's before we have the informations MCS or total service cost, and also waiting line cost you can calculate by lambda WCW. So once you summarize by the informations, you can get the total cost. So later we can calculate by time in the queue or in waiting line by using total cost is MCS plus lambda WQ CW. So it's quite easy, and the information is be connected by each other to calculating the total cost, total service cost, and also the total waiting cost. So for example Arnold estimate the total of the customer waiting time in line is the $50 per hour. So we can calculate by this information. So it's quite easy. Total daily waiting cost is 8 hours per day. So you multiply by lambda, WQ, and CW. So that's why we have these informations by last slide. So we already have the informations. We have the 8 hours. We have lambda 2 and WQ 2 per 3. And we have here CW 50. So we can get the informations if the $533 per day. So this is our information of total daily waiting cost. So that's why I'll tell you about this quite easy, very, very easy. Also about the mechanic wait in the $15 per hour. So we can calculate by total daily service cost. So we already have the information, 8 hours per day and MCS. So we already have the information, MCS. So we can get the $120 per day for the mechanic wage in per hour. So this is the total daily service cost. Also, we can calculate the total cost of the system by using the total daily cost of the 20 systems if is the $500 plus $120. So we can get the $653 for cost of client system. So we can get the information or calculation by using the total daily waiting cost, total daily service cost, and also total daily cost of the client system. So it's easy. Here, so we have the example. Arnold is thinking about the hiring repair mechanic who can install movers at a faster rate. So that's why that follow Poisson distribution, we only have two parameters. We only have lambda and mu. Lambda is the 2 cars RV per hour, and the mu is the 4 cars surface per hour. This is our information. So same with the previous slide, we can calculate by L, W, P0, WQ, LQ. So here we have L, we have the one car in the systems on the average. So this is our information. So once we calculate the W, we can get the 1/2 hour that an average can spend in the system. So this is our information. Similar, you can calculate LQ, WQ, and the P0. So you can calculate how many car waiting line the average, how many minutes average waiting time per car, how many probability or how many percentage time mechanic is busy, and how many probability there are 0 cars in the system. So here we can calculate easy with the same information. Same as well, you can make the sum of simulation here from the K start from 0 until 7. So here we have this criteria to calculate the more than K cars in the system. So once the N greater than K, we can calculate by 2 divided by 4 power K plus 1. So this is our simulation. We can finding the information is how many cars in the system can be handled by the server. Here, stems like the previous slide, it's easy as well. So we can calculate the customer waiting cost in the SAMS $50 per hour. So SAMS, we can using the total daily waiting cost. So, we can get information of 200 per day. Also, we can get the information how to calculate the total daily service cost. So we can get the information is $160 per day. And we can calculate by total cost of the system. So we can multiply by this information. Sorry, you can summarize by this information with the total daily waiting cost plus total daily service cost. So we can get information of the total daily cost with the $360 in the client system. And we can calculate as well the total time spent waiting for the 16 customers per day was formed. So we have this information, 16 multiplied by 2 per 3, we can get the information is 10 hours, or you can go with the 11 hours. And here we can get the information of the now current issues. We have the 16 cars per day, and also 1 per 4 hours per car, quarter hour. And we can have the 4 hours. So we can calculate information how to calculate the total daily system, and we can get this information, and we can get the information with the $200 to get the total system cost with the new mechanism, resulting in significant savings with our information. Here we have the issue about how to enhancing the queuing environment. First, about the reducing waiting time is not the only way to reducing waiting times. And second, about the reducing the unit waiting cost will also reduce total waiting cost. And about the last point, about the might or be less expensive to achieve than reducing either of W or WK. So this is the type to enhancing the queuing environment or to enhancing the line process system in our queue line. And how if we have more, we have the multi-channel models, so we can using these informations, big M, and small m, MMM. So we have 3 parameters here. First, about the number of channels open, we have the M, small m. We have lambda, similar the average arrival rate. Also, we have mu. Mu means the average service rate at the each channel. So we have 3 informations, M, lambda, and mu. And it's also quite easy to calculate the probability. We have the P0 here. So it means the how to get the probability that there are 0 customers in the system. So you can calculate by this information. So we have sigma. Sigma means the summarized from the start from N0 until N minus 1. So how many M meter? So you can multiply, summarize by that. And also this categorized by 4, mu should be greater than lambda. to calculate the P0. And this information, some basic assumptions as in the single channel model. So this is our assumption. So we can analyze by this information. So how to calculate the L? If we have the MMM, the exponential service time, so we can calculate like this, the average number of customer or units in the system. Also, we can calculate the average time with the W. We can get the information is lambda divided by L divided by lambda for calculate the waiting line per serve in our system with W. And same, we can calculate the LQ, means the average number of the customer with this information. We can calculate as well by using WQ. We also can calculate our probability for our row. So similar that if you're using the single channel or multiple channel, this, the information that we can get should be similar. We're using the LQ, WQ, row, L. So this kind of information to calculate the waiting line theory. Here, similar with the Arnold's Mulberry Shop revisited with the same information. Arnold wants to investigate opening a second garage bay. So we are here, we hire a second worker who works at the same rate as his first worker. And the second, we cast the customer arrive rate remains the same. So we can calculate this information. And we can calculate the number of probability. So we can calculate probability 0.5. It means the probability of the zero cars in the system. So we can calculate like this. Once we have information, the N and mean K, so you can calculate easily. So that's quite easy if talking about the quiet line system. Here, similar, we have to calculate the L, W, LQ, and the WQ. So once we calculate the L, we can get the information with 0.75, the first number of the cars in the system. And we can calculate the W, so we can get the 22 half minutes of first time a car spends in the system for W. And also we can calculate 0.083 and third number of the cars in the queue. So this is our LQ. And how to calculate the time car spends in the queue. So we can get information is 2.5 minutes for WQ. So it's quite easy, similar. Once we using the Quantitatory, we have to calculate the P0 first. We'll calculate the L, W, LQ, and WQ. So once you using the MM1, MM2, MMM, so we can calculate that information. Here our informations for the level of service. We have three informations of three variables. First, one mechanic, two mechanics, and now last one is about the one fast mechanic. So here we have 5 observation. We have the P0, L, W, LQ, and WQ. So we already calculate about that. So we can calculate how once we have the one mechanic, so we have this information. How we have the two mechanics, so we have this information as well. And last but not least, we have the last information about the one fast mechanic. So we have this information. So we can calculate which level of service is we needed in our business area. And by adding the second service, we reduce the waiting time in the line, but will increase the service cost as a second mechanic needs to be hired. Similar with the previous slide, we can calculate the total daily waiting cost. We can calculate by total daily service cost, and we can calculate the total daily cost of the system. So it's quite easy. So we can get information. We have the 8 hours per day for the working hours. For it depends. If you think that you have 9 hours, yeah, you can put 9 hours per day for working hours. So we have information about the lambda in this question. We also have the WQ and CW. So we can get information is $30. So in Korea, the working hours is 9 hours per day. So it depends on the country. Similar, later you can using by the Excel, by the KM solution for Arnold's multichannel example. Here, that's because we have this information in Poisson distribution. We have lambda, mu, and how many servers do you have to maximize the business. So here, for example, we have the variable rate for lambda is 2, service rate mu is 3, and for example, we only have 2 servers. and the queue line. So we can calculate the information about the row, LQ, LWQ, W, and the P0. So it's easy. So you can compare the number of the n here. Start from the 0 until 7 or 0 until 10. It depends on you until you can get the lowest probability for our simulation. So it's quite easy. Here we have the arrival rate, surface rate, and number of servers. So I repeat link. So about the homework, wait,